Good afternoon. My name is Yongqiang, and I'm from Monash University. So today I will talk about our work, Supercharge compiler engineering with large language models. Definitely, we have other work without large language models, but today we'll focus on those with large language models, some preliminary work. I guess you have heard a lot about compilers this week. So compiler is a critical software for computers. It translates high-level programming languages into machine code that a computer process can execute. So almost all software we are using now today, from operating system, AI infrastructures, productivity software, mobile apps, rely on computer compilers to function. So undoubtedly, compilers are the fundamental building blocks of the modern computers. So in the past decades, it's a kind of common objective for developers and researchers to build good compilers. We hope that compilers can effectively produce a correct, optimal machine code. But unfortunately, because of the complexity of the compilers, it is challenging to achieve this goal. This is because compiler is very complex software. The input space is huge. The compiler also need to handle a lot of language features and also optimizations. Specifications are also updated, and sometimes we don't have some specifications. So all these kind of things need to be considered by compilers. So as a result, we now have a very buggy, some suboptimal, inefficient compiler sometimes. For example, 10 years ago, GCC actually miscompiled the Linux kernel. As a result, the scheduler in the Linux kernel cannot function correctly. So to improve the quality of softwares, especially compilers, massive efforts and in-depth domain knowledge can be made to these goals. And for example, researchers have proposed various techniques such as formal verifications, testing, program synthesis to enhance the compiler reliabilities and performance. If we search them in Google, we can see that actually there are around 1 million papers have been published. And for engineers, they are strive to improve the compiler structures and toolings. In LLM, around 1,000 pull requests have been submitted every week. So these efforts demonstrate the commitment of the research communities and the industry participants to improve the quality of the compiler techniques. So our research want to help compiler developers to build better compilers with fewer human efforts. For example, specifically, we want to know how can we facilitate the compiler engineering with some kind of automatic technique. So let's look at a typical workflow in compiler engineering. So basically, in general, compiler developers need to design optimizations, and then they need to write some code, do the implementations, and test it. And eventually, we hope that everything good we can integrate into compilers. But during the test cases, sometimes compiler developers need to run the test cases, and if anything of these tests fail, developers need to do the debugging. So in the past, there have been many works focused on testing part. For example, this year's most influenced papers, and this year we also have the new papers, leverage large models for compiler testing, published by Yubo and Shaohua. So in this talk, I want to talk the other two perspectives. Specifically, I want to introduce our work on the other two phases. One is how to design optimizations, and another is how to do the debugging. So I will show some preliminary work that we use the creativity of the larger models and also the advantage of the pure technique to help us to achieve these two goals. So let's start with the first one, so optimizations. So in compiler, peephole optimization are common type of optimizations that involve replacing a small sequence of the instructions with a more efficient one. For example, given this code, every time we will go to a small windows. For example, in here, we are optimizing these two instructions. We'll check whether these two instructions in these small windows can be replaced with the more efficient instructions. So if not, we will go to the next one, and eventually we found that this code and multiple, they can be replaced with one sequence, which is shift left by 3 bits. So this new sequence of the instructions is more efficient, so we will do the replacement. So peephole optimizations are widely used in the compilers because they can significantly improve the performance of the generated code. And the generated code is more efficient and non-equalizations, which will enable the further optimizations by other compiler optimizations. And because it's important that developers are always looking for new peephole optimizations, we can find this from the history of the GitHub history. But actually, it's not easy to design these new optimizations. There are three major methods to achieve this. So the first one is rely on the manual efforts. We manually design these peephole optimizations. Developer leverage their in-depth domain knowledge and look at the existing code patterns and think about how to optimize. This kind of method is time consuming and require a lot of knowledge based on this, a lot of knowledge of the compilers. And this is hard to scale, and this is not easy to maintain. So the second method is to leverage difference testing to find the peephole optimizations. We try to find the optimizations that will be, for example, used in one compiler, but they have not been used in other compilers. This method has been used in the past and found many bugs in GCC. They are not in LLM and vice versa. However, this method actually requires two implementations of one compilers, and also difference testing is not to find new optimizations, but actually it's only find the optimizations that's not implemented by this optimization, but not implemented in this compiler, but actually they are already existing other compilers. Super optimization is the third method. It's another way to find the optimizations. It uses exhaustive search or problem synthesis to find new peephole optimizations. For example, super, the state-of-art technique, it has been used to find many peephole optimizations in larger models, not in larger models, in LLVM. And the major limitation of this kind of method is that they are very computationally expensive, and as a result, they do not scalable to all the language features. For example, super actually does not support the memory ones, floating point, and vector instructions. So if we look at all these three methods, we can see that they all have their limitations. These kind of methods either lack of scalabilities or have the restrictions or the optimizations that they can find. So we would like to see that how can we facilitate this compiler engineering with automatic approach, specifically in this to find the new optimization in the peephole optimizations. So our insight is twofold. First, larger models have shown great potential in creative explorations and reasonings. So if we leverage this kind of creativity in larger models, we can help developers to design new peephole optimizations. Unfortunately, this is not that reliable because larger models still generate a lot of unreliable answers. A lot of answers are incorrect, which is not helpful for compiler developers because in compilers, we definitely need some strong correctness guarantees. So on the other hand, we notice that the formal verifications, they are powerful tools for developers, and they can provide the correctness guarantees for optimizations, but they don't have the creativities for new optimizations. So we would like to leverage the advantages of both larger models and formal verifications to help compiler developers to design new peephole optimizations. Specifically, we first ask larger models to generate new peephole optimizations. But remember that because of the hallucinations or all the limitations on larger models, we don't know whether the new optimizations are correct or not. So fortunately, formal verification tools can provide the correctness guarantees. So we can leverage these advantages and ask it to do the verification to verify that whether the new optimization from the larger models, whether it's correct. And if not, we can always use larger models, give some feedback to continuously optimize this part. So in summary, in this part, we leverage the creativity of the larger models and the strong correctness guarantee of formal verifications to discover new verified peephole optimizations in compilers. So based on this insight, we propose LAMPO. I will show you very simple examples. So first, this is a Rust function, it's clamp. It will clamp a sequence of side 32-bit integers to an onside 8-bit integers. So we first get the RR of this function. So this RR is too large for larger models to handle. So we do some extractions. We extract the dependent sequence from the RR and make them to a small functions. In this part, we also exclude the all invariant ones, and then we feed this sequence to larger models and ask larger models to produce a correct and optimized code as a candidate. It's still candidate because we don't know whether it's correct or not. And here is the output from larger models. And then we feed this candidate to the optimizers of the LLVM, and LLVM tell us that actually this candidate is wrong. There's errors, and we feed these errors again to larger models and ask to generate the correct one based on feedback. So here, now this time, larger model give another candidate. We feed this candidate to optimizers again, and also we ask to do the interestingness check and the correctness verifier to check whether with these new candidates have fewer instruction count and whether it's correct. And in this case, it passed these 3 checks. We're happy with this. So we think that perhaps this is a very likely new optimization we found, and we put into potential missed optimizations. So if we look at the difference, we can see that originally the sequence is x smaller than 0. It have a new branch to compare it smaller than 0. Then if it's smaller than 0, do something. So this kind of branch actually is not optimum. We can larger model tells us that we can replace the upper one to a lower one, and the lower one actually is more efficient because it have fewer instruction count and avoid the conditional branch. So note that the previous work, like Super, does not support LLVM on-site minimum, so that it cannot find this bug. So this is LAMPO, the first automatic technique to discover new optimizations in LLVM, and also using the formal verifications. In our around 7 months development and testing, we found that 26 new peephole optimizations, and 15 of them have been fixed by by the developers or compilers, and 6 of them have been confirmed. Yeah, so this is the results. There are some duplicated ones, and there are some that developers say that they won't fix. We also actually find a bug in the alive tool, which is the translator verifications. And in contrast, the baseline can only find 9 of these 26 bugs. We investigated the performance of the different larger models in this case, and we found that actually reasoning models perform better than the others. If we also build a small benchmark. They are used on 25 missed peephole optimizations after the cutoff date of this kind of 6 models. They have been confirmed, so we can know what's the result between existing technique and our technique. We found that LAMPO can detect 7 out of the 10 missed optimizations that cannot be detected by existing technique, which is super. So we do some study about the impact of the feedback guided loop in LAMPO. Specifically, we remove this feedback loop here. And we found that if we remove that, up to 7 missed optimization cannot be detected anymore. So which means that the feedback is kind of an effective approach to guide the larger models, at least in this task. So here is a summary of first part. So in this work, we talk about the peephole optimizations and how we leverage the creativity of the larger models and the correctness guarantee of the verifier to discover new verified peephole optimizations. We detect 26 new optimizations, and many of them cannot be detected by existing work. So we talk about these optimizations. Now, let's talk about debugging part. So the test case generated by automated testing technique can usually be very large. It may have thousands of lines of code, which is very hard for compiler developers to debug. So because of this reason, compiler developers in C, Mozilla, and also Rust, they all explicitly require us to report a minimized bug triggering program. So this kind of minimal bug triggering program usually may just have tens of lines. They are much simpler and easy to debug. So an automatic approach to transfer this large program to small program called program reduction is kind of technique that automatically reduces the bug triggering program to a smaller ones. So given program and a property of interest, for example, here, if we claim that the property interest that it can trigger a bug by produce a hello world. So by program reduction, we can gradually remove the code and only keep the minimum ones. So there are a lot of program reduction tools or program reducers. They have been widely used by compiler developers. For example, in C, specifically we have C reduce. It's a language-specific reducers. So it have a lot of the C-specific transformations, like function inlining, constant propagations, loop unrolling. So with all these transformations, we can transfer the C program from large bug triggering program to a very smaller one. However, unfortunately, these kind of transformations, they are specific to C, which means that they cannot be applied for Java, Rust, and JavaScript, which means they are hard to generalize these kind of transformations. So Persis and Vulkan, they are language agnostic reducers. They leverage a lot of syntactic transformations like node replacement or identifier replacement to do the transformations. These kind of transformations, they can be applied to almost all the languages. However, the result is that they can do transformations to all the languages, but the result is not as effective as those produced by language-specific reducers because it cannot leverage the language-specific transformations to further reduce the program. So in summary, language-specific reducers, they are more effective, but they are hard to generalize. The language agnostic reducers, they are more generalized, but they are not effective as the specific ones. So we would like to know whether we can combine the advantage of these two kinds of reducers. For example, here, can we borrow the semantic transformations from the language-specific reducers to help the language agnostic reducers? For example, every time after the program is reduced by language agnostic reducers, we feed them to the borrowed semantic transformations to produce even smaller programs. So we think that this is possible, specifically with the large language models, which can help us to achieve these kind of transformations. So in this case, we leverage the creative exploration of large models to do some effective semantic transformations. And meanwhile, we use the language agnostic transformations from Persis or Vulkan, and eventually we achieve an effective and language agnostic reducer. So this is LPR, the LLM-aided program reduction. So giving a bug triggering program, we feed them to Persis. We can generate a relatively small program, and we put the results to larger models. And we use larger models. We ask it to take a look of the C-specific transformations and try to replicate these kind of transformations in other languages. For example, function inlining, constant propagations, and loop unrolling. And we feed these results to Persis, and we continue to loop again until we can generate a minimum bug triggering program. So here is a very small example. Assume that it triggers a bug in JavaScript compilers, and the root cause is divided by 0. So if we feed this result to Persis, we will have we can delete this gray lines, and this is the result. Persis cannot further reduce it because we need to inline a JavaScript function, which is not achievable for language agnostic reducers. So we first ask ChatGPT to tell us which function can be inlined. GPT tells us perhaps function foo can be inlined. Then we ask it to do the inline. And after inline, we can feed this to persist, and we can have another small results. And here we can do another transformations, for example, which constant can be propagated. GPT tells us that C and D can be propagated. We ask GPT to do either of them, then we can propagate, delete one line. So eventually, after persist, through the loop, we can have much smaller results, so which only have 3 lines. So this is on left is the original code, middle one is reduced by persist, and eventually with larger models, persist and Vulkan have produce another smaller result. We implement 5 proposed transformations. They are common in C reducer, and actually it's very easy to define new transformations. You just need to serialize all natural languages, and sometimes you can leverage the example of existing implementations from the existing reducers. So through the results, we find that on C languages, LPR actually achieves significant smaller results than other language generated reducers, for example, persist and Vulkan. And actually, LPR and Vulkan actually they achieve the comparable results with C reducer, which is very hard to achieve. Actually, you can see the gap is very, very small compared to others. And for other benchmark, Rust and JavaScript, LPR achieve much smaller results than the persist and the C reduce. And if we take a look at the efficiency of LPR, we can see that each query, they may take around 39 seconds on average, and it may take like 41 LM queries on average, and actually a lot of time, around 1/3 of the time, is spent on waiting for the larger model's response. So persist is actually, LPR and persist actually, they are open sourced. We have a family of persist. It's well-documented tool. It has multi-language supported. It's widely used by a lot of companies and compilers, compiler developers. So I think in Uppsala we have SFC, another technique to help us to achieve program reduction, especially on the canonicalization part, not only just minimum program, but also help us a lot in deduplications. And next month in ASC, you have lateral template-based language model, template-based language agnostic transformations towards effective program reductions. And last year we have weighted data debugging, counter-based data debugging in EC, and Vulkan, which published 2 years ago. Actually, based on the idea of program reduction, we also proposed a Katan, which is published in EJK and ISTA. It's a simple yet strong baseline for compiler testings. In 7 months, we found, not in 7 months, in 7 compilers, different compilers of different languages, we found more than 300 bugs. And a lot of them have been confirmed and fixed. So let's go back to the questions, like how can we facilitate the compiler engineering with automated approaches? We believe that one approach is use the creativity of larger models and also use advantages of existing technique. Combine them together, we can discover new verified peephole optimizations. You can achieve effective and language agnostic reducers. We believe a potential way, this is a potential way to help us from the buggy, suboptimal, inefficient compilers to finally achieve a relatively strong optimized compilers. Yeah. We also have other work in testing the AI infrastructures, TVAM and OpenVINO. We found around 300 bugs in these AI compilers, and actually they are just accepted yesterday on EC. We have a prototype for Solidity compilers, which is also accepted. Yeah, feel free to chat with me if you are interested in this work. I'm happy to share some details. So finally, I want to thank a lot of my collaborators, Chen Niansong, Zheng Yangxu, Hong Xu, and Mengxiang Zhang. They are my lab mates and supervisors. One was in Waterloo. Without them, we cannot have this work. So yeah, this is basically our my talk will introduce the compiler engineering, the work to detect new optimizations, and the work to help us to do program instructions. And yeah, I'm happy to answer any questions, and here and offline. Yeah, thank you.
We have 4 minutes for questions. Please come to the mic.
Sorry. Hi, Yongqiang. So I wonder, what's the oracle for your minimization? Meaning that, how do you quantify whether minimization is correct or not?
Okay, so to achieve this, we need to write a property check to check whether this code still triggers the same bug.
The same bug.
The same bug. For example, when we have the original large program, we have like an error message. We always check this error message.
Okay.
But that's just one part. We also need to check whether the minimized program is still valid program. It still does not have the undefined behaviors.
Okay.
It's a very relatively large script, but the idea is still trigger same bug.
Right, but what about the accuracy of LPR? Because I think that's the part that didn't mention. The accuracy, like, does LPR always produce a correct
good
output?
question. No, so that is also quite advantages of the using larger models in LPR, because even in traditional program reductions, we do not guarantee that we always generate a valid program during the transformations. Because in the transformations, if you only have the syntactic information, the transformation may not break the semantics. So it's acceptable even without large models. And now with large models, it's produce a incorrect one. We just disguise it and put in another loop. So it's a limitation on larger models, but it's kind of
right.
Yeah.
Okay, thanks.
Okay.
I have a follow-up question. So for the LPR, indeed, it doesn't have to semantically do the same thing as long as it also introduces the bug. But for the peephole optimizations, you do want it to still produce the optimized piece of code that it's semantically the same. How do you guarantee that?
So for the LPR, we do a lot of transformations on the syntactic part. For example, if we have a statement list, we will just remove part of the statement in this list, but still it is list. I think in the transformation, it automatically have different semantic.
No, for the first optimization set, the peephole optimizations.
Oh, okay.
There you do want that the semantics are preserved when you do the transformation.
Yeah. So every time after the LLM think is correct one, and we have interesting check, we feed them to allow to. Allow to is kind of verifier to verify these two optimizations. They still have the same semantics. So we rely on allow to. That's the reason we currently only have this technique in LLVM instead of on C. So kind of limitation for this work.
Okay, thanks.
Thank you.
So with the data debugging thing, the program reduction, right? So you say that you don't care about the correctness because if the property of the test fails, you just try again, right? My question was, parentheses and C-reduce, they guarantee a property of one minimality. How does that guarantee hold when using LLMs?
Yeah. So let me correct my words. So we care the whether program is the generated program is still valid or not. We still care them because if you care a lot of invalid programs, actually we are wasting a lot of time. But the good thing is that we have some kind of tolerance is still acceptable because we can discard it and feed them another loop. And for the one minimality, we also achieve this actually because if we cannot further remove it, we stop it which means that it's one minimality. The good thing about the LPR and also the Vulkan is that actually we use some kind of way instead of achieve one minimality. Actually, we do one minimality means that we cannot remove any one elements from tree. But sometimes if we remove 2 using the Vulkan and our technique, actually we even achieve a much smaller results. So we kind of try to escape from the local optimum to achieve 1. Our paper are online. You can take a look and chat with me anytime. Thank you.
Great. Let's thank speaker again. And
Thank you.